Olivia's up next, and if you fancy sticking a few quick shots at his arm, you're an idiot.
I want to come up this boy because I feel like we've been waiting for this day where it feels like a lifetime. And in the past week, we've been underneath the patient with me, and I would like to have a chance to show him that hopefully I was worth away and doesn't hurt his dick. So the boy I want to couple up with is Chris.
Well, you know, it's Corey choice. I say choice, it's either Sam or Reddy on camera 2.
I want to couple up this boy because he has got a heart of gold and there's not a moment in the day that he's not making everyone laugh and just brings out the best in people. So the boy I want to couple up with is Sam.
Be shy. Things work out, don't they, eventually when you give it time and you be patient and stuff. So no, I'm happy. Like at the end of the day, I always wanted to be coupled up with Liv, and it's taken us a while, but we've got there, haven't we? Next time on Love, the recoupling leads to regret. I can't be myself. I'm too honest with you. The last effect I felt I had. I just don't want you to keep holding your guard up with me.
I want to see how many episodes there are of this.
Yeah, it's on live right now and there's someone on. Just a heads up.
Okay. What time is it?
Almost 5. I'm just
11 minutes.
yeah, that doesn't mean they can't hear the audio though. I was just giving you a warning to be polite. Nope, that won't work. Do we have a book in here, something like that? Not that book. Need that one. There we go. Let's see if that works. Nope.
Bye-bye.
Bye, baby. This, and then okay, that should work. Can everyone in the video, anyone that's, or the one viewer that's here, I suppose, can you see the whiteboard pretty well? Just want to make sure that it's an optimal viewing window before we get started on today's session. If my laptop falls over, have sympathy. This camera angle is a nightmare. Okay, let's see what we got here. Perfect. Now let's see my cat on my markers. All right. So there's one person in here I figure I'll give you the benefit of doubt and that you're here because you want to learn early, not because you have nothing else to do. So if you'd be oh so polite to type in any concepts you're struggling with for the current material into the live chat, that would be greatly beneficial for both of us. Far past sequences, like a divergence test, convergence test, stuff like that, limit comparison test, when to use each one. Limit comparison has a pretty specific usage. Like, I think that you can use the limit comparison test. Well, I don't think I know. I know you can use the limit comparison test to, instead of plugging in values for like a direct comparison test. But I'm just going to go over a little bit of review before we jump into all that and just make sure that, you know, since we're starting back from the break, everyone is able to still, you know, do math. So this is a quick little integration right here. I just did it for fun because I don't know. This Corona stuff has given me too much free time. But this right here is pretty simple. It's just integral of e to the x to the negative second. So I'm sure there is a way you could do this logarithmically, but that's overthinking it. And honestly, a u substitution in this situation is going to be the most efficient method of integration. So I've worked this one probably a couple times throughout the semester, just because I know that right after integration by parts, this is a common misconception that this would be integration by parts. Just like another one that could be, that a lot of people would probably assume is integration by parts would be something like the integral of cosine times sine, which, again, not all that bad. So let's do this. So cosine x sine x, and I know this is very basic review. I'm just kind of, I figure if more people join, at least one of them will know how to integrate. So I'm just going to go over like this, and then I'll kind of jump back in on series, and we'll see how the whole deal goes. So let's think. The derivative of sine is cosine, right? So what if we say u equals sine of x and du equals cosine of x dx? So then, you know, you just solve it like, solve it in terms of u. You'd end up getting the integral of u du, which is equal to u squared over 2 plus c. And we know that u is equal to sine of x. So finish integrating this. And again, this is just review. So, I mean, I think it's always helpful to have review, but if you don't need it, then you can play on your phone for another minute or so, because I'm just going to be going over this. So this is just very, very basic, by the way. Like, you should definitely have the tools in your arsenal or toolbox, whatever you want to call it. You should be able to integrate that like blindfolded. I mean, that's something we learned in the first week. So now to get something we're learning in the 8th week, 9th week, I believe. I'm not entirely sure, but now to get back to what we're actually doing in class, infinite series. So I'm just going to go over a few generic definitions, make sure everyone's aware of how to approach an infinite series. And again, this is all review, so I'm just doing this because it says there's one person that came early. I don't know if you're actually here or not because you haven't responded to the video at all, but I mean, at least you're here, right? All right, convergence, divergence of an infinite series. So telescoping series isn't anything horrible. Oh, here, this one's actually kind of neat right here. So this is just and you know, again, I'm going over like pretty much a test for each new way we know to approach an infinite series. So I'm gonna set up this telescoping series right here for y'all. And this one could be kind of hard to figure out, because this one, I don't believe it's actually asking for divergence. I think it is asking for infinity. Well, yeah, well, this right here is asking what the let's see, sequence of partial sums is. And this isn't really something you need to know how to do, but like it's something to keep in mind. So let's remember decomposition of partial fractions first, because that is going to be crucial to this whole problem right here. So we got 1 over k times k plus 1. Sorry if the whiteboard's rocking. I don't know who made this whiteboard stand, but it's not very sturdy. All right, so this, now we remember, since these are both linear functions, we can do this. A over k plus b over k plus 1. So this should look very familiar to you because this is exactly what partial fraction decomposition was. So now we're going to end up getting, let's see, 1 equals, we're going to multiply both sides by the denominator of this. So then times k plus 1. Okay, good. This is still all in the video. So now we're going to have 1. This k is going to cancel. So we're going to have 1 equals a times k plus 1 plus b times k. So we'll just write that as bk. All right, so that right there again, just decomposition of partial fractions. So now let's see. This problem did give us a little bit more to work with, but not too much. So let's just plug in a few values for k in this situation. So let's start with k equals -1, because we want to solve for a and b. We're solving for undetermined coefficients. You guys have done a lot of this, but in next year, if any of you are taking differential equations, which I would highly recommend taking after this class, if you know this stuff, you're going to be at a major advantage. So I would practice this a lot over the summer if you're taking differential equations or a course like that. But anyway, back to the problem. If we plug in -1 for k, then that's going to give us 1 equals a, so k equals -1. So -1 plus 1 is just 0. And then plus b times k, right? So then we know that 1 equals, let's see what this is, b times k. So thus, b equals 1 over k. Right, now this is probably seeming strange to you guys. I'm not sure how much you've really gone into all this. I'm sure a lot of it is quite tricky for you because, obviously due to the current circumstances, learning is a lot less personal. But if you are having trouble with this, just message me in the chat. This shouldn't be too bad. It's just a telescoping series, If you guys remember the definition of a telescoping series, then this should look pretty familiar to you actually, because once we get the sequence of sequence of partial sums, then we are going to be able to solve this summation right there, this infinite series, my bad. So we know that b equals 1 over k. So now if we want b to equal 0, then we just say k equals 0. So then we get 1 equals a times 1 plus 0. That kind of looks like a Q. I'll fix that. So then we get 1 equals a. Meaning, strange. Okay, well, what this is going to give us right here, that is strange. I must have made a mistake. Yeah, I definitely did. Because that right there, my apologies, guys. I did make a mistake. Because I was solving in terms of variables instead of terms that we can work with. So I'll just run through this again real quick, fix my error, and we'll resume the review session we're doing right now. So we got 1 equals A times K plus 1. I already figured out my error. Plus B times K. So let's start out with K equals -1 again like last time. So that's going to give us 1 equals 0 minus B. That's my mistake. I forgot to plug in -1 for the K next to the B. So now we're going to get B equals -1. So then the next thing we do is K equals 0. So for K equals 0, we're going to end up getting 1 equals A. So just A equals 1, essentially. So now we've got A equals 1, and we know that B equals -1. So let's make this a little nicer right here. So we got B equals -1, A equals +1. So now let's plug this back into our formula. So this right here, and shoot, what do I think? I can add more details to this problem in case this isn't making sense to you guys, because I don't know how much y'all are actually studying. I would assume it's probably not a whole lot. I don't say that because I doubt you, but I say that because I imagine that most of the country right now isn't studying actually. Okay, well, this right here is equal to 1/2 plus 1/6 plus 1/12 dot, and then something equals 1. All right, so now for the next part, we already have our A and B values, so let's just plug them into the equation they gave us that we made here by, let's see, a new person's in here, but we made this equation by partial fraction decomposition, which is the method of integration from that we did that you guys reviewed for a lot on the last test. I'm sure you guys remember where you cancel out the denominators, blah, blah, blah. But honestly, with this information right here, part of the reason I didn't include this is because I'm sure a lot of you are just, figuring this out on your own. Like, it's not too hard. You could do a couple things to move stuff around, but this is probably like most tried and true best way to solve this. It will give you an answer every time for a type of problem like this, and there won't be a whole lot of uncertainty, which is always a plus. So let's plug in A and B now. So if we plug in 1 for A, then we're going to get, and this is plugging into our original thing right here, right? So we know that, actually, you know what? Is it cool if I erase some of this right here for the one person watching? Yeah, maybe. Just to be clear, okay, you guys can hear me. All right, so A equals 1, B equals -1. Let's write that. I probably should have wrote that. Shouldn't have erased that, but that's okay. So we know that the infinite series, where K equals 1 as it approaches infinity, for the function 1/K times K plus 1 is equal to, let's see, A, so 1/K minus 1/K plus 1. And let's check our answer real quick. So that is, that's right. I almost forgot the golden rule. All right. Oh, I almost forgot the entire purpose of a telescoping series because I was being dumb, but limit as K approaches infinity. Yes, I think we will do that. And the reason, guys, we did all of this stuff up here is so we could get it into two, pretty much linear reciprocal type functions so we could see the cancels and kind of map it out. So let's start it with, well, we can just write this down here, can't we? Limit as K approaches infinity, and this is the telescoping series, for the function 1/K minus 1/K plus 1. Let's see if I can, don't want to mess with that. Wait a minute. Have you guys not been able to see the bottom half this whole time? Oh my God. Okay. There we go. equals, let's see. So let's plug in a few values for k. So if we plug in 1 for k, then we're going to get 1 minus 1 over 2 plus, and this is a series, so I got to put the little thing there. But 1 plus 1 over 2, 1 minus 1 over 2 plus, now we're going to plug in 2 for k, which is going to give us 1 over 2 minus 1 over 3. And we're going to add on, let's see, we're going to plug in 3 for k, so we're going to get 1 over 3 plus blah, blah, blah. And you're going to notice that the middle terms here cancel. So negative 1/2, positive 1/2, negative 1/3, positive 1/3, which would mean that we are only left with the first and last terms. So our first term is obviously 1, right? And then our last term is going to be negative 1 over infinity plus 1, which is really just 0. So let's double check that. Yeah, okay, I guess I got a little bit ahead of myself, but yeah, okay. So the whole point of this was limit for S of n, which is the sequence of partial sums for n approaches infinity. And again, we just did all this. This right here is the sequence of partial sums. So that is going to be equal to 1. So we just proved basically what they started with. We're like, okay, so you guys gave us this telescoping series, told us that it was equal to 1. We just proved it by showing that the sequence of partial sums also converges at its sum of 1. So that's telescoping series. I'm just kind of going over a generalization, like a quick review, guys. Like I'm really just trying to get all the tests, make sure you guys all remember what we kind of left off on, because I know that breaks tend to take a toll on memory of calculus. I remember when I took Calc 2 that we had a break for, what was it? It was right before like finals and all that, and I had to force myself to study because I had like a 92 in Calc 2, and that final was worth 50% of the grade. Still finished with the A though. Yeah, so at least the final in this class isn't worth 50%. I'm sure some of you wish it was, but you actually don't. Unless you just don't like going to class. And I mean, honestly, for classes that do 2 tests, like a midterm and a final, they normally don't check attendance. But you didn't hear that from me. A times r to the k minus 1. Okay, so this right here, I really wish we were like I could. Someone in the group chat, or you don't have to, I guess, but I would like you to tell me what kind of infinite series that is, if you can. If you can't, just type pass, because this is supposed to be somewhat interactive. I mean, if you guys prefer me like just going over everything in a review type format, then that's okay. But who can identify this type of infinite series? You probably saw something similar to this in pre-calculus, where we define. Yes, nice, thank you. Geometric, exactly correct. So geometric, an infinite series, geometric series, the sum, if it converges, is, what is that? A over 1 minus r. And this is only going to have a sum if the absolute value of r is less than 1. If the absolute value of r is less than 1 for a geometric series, then we know that it converges, and we know that its sum is going to be equal to a over 1 minus r. So the hard part about geometric series is there's a lot of exponent rules. So let me see if I can find an example here real quick that could be pretty interesting for us to work through. Just because I know a lot of you guys, I know a lot of students in general actually don't tend to be very comfortable with exponents, which, I mean, I guess I get it, but they're not too bad. We'll work through a couple. I think I've got one really good one somewhere in here. Okay, so I may not have it in my notes, but you guys definitely have it in your textbook. So what I would recommend is going through the second, and like not all of them are going to be hard. Keep this in mind. Like here's just a real quick, easy example. So example, this marker's dying. Let's see. So real quick example would be something like, oh, here it is. You know what? I found it. So we got k equals 0 as it approaches infinity. Right? Then we've got, let's see, 1 over 2 to the k. Right? So this right here is, you may not initially view it as a, as a geometric series, but it definitely is. And the way that we can kind of approach this one is that we can say that this right here is equal to the infinite series for k equals 0 as it approaches infinity. And we know that 1 to the k power, so 1 to any power for that matter, is okay, I know that it's using my camera, not my phone. But anything, 1 to anything other than 0 is going to be 1. Because, you can multiply 1 times itself infinitely. It doesn't change the fact that it's 1. But we can, so then we can rewrite this whole expression right here as 1/2 times k. Now, there's two forms for this. This is technically an equivalent form, but we want k to equal 1. So a way that we can do that is we practice like manipulating, that's a really gross k. We practice manipulating exponents. We did this in algebra 2, like way back in high school, if you all remember. But this right here, let me show you guys how this works. This is pretty cool. So let's see. If we say k equals 1, right, as it approaches infinity, so we need to make this equal to that. So if k equals 0 here, right, so then 1 over 2 to the k, 2 to the 0 is just 1, so that's equal to 1. So now the way we'd approach this, and again, same deal with here, we just simplified this one, but k equals 1, and then what we're going to do is we're going to rewrite this as 1/2 times 1/2 to the k minus 1. And the reason we can do this is because of exponent rules, right? So I'm sure a lot of you guys probably are having that light bulb moment right now where we go, oh, so we can rewrite this as just, we'll just rewrite the function first, right? We'll forget about the series just for the sake of the math, we'll work this. So that is equal to 1/2 times 1/2 to the k times 1/2 to the negative first. And, negative first just means we put the current, we flip that, right, for a fraction. So then what's 2 times 1/2? That's going to give us 1, right? So then this 1/2 to the k, still equivalent, still for game to work with. So now we know what the r value is, we know what the a value is, we can solve this. So let's plug it into our equation. But first, let's check if it converges. So this is r in this situation. The absolute value of r is indeed less than 1. Or, wait, I might have got that backwards. Yeah, less than 1, less than 1. Nice. Okay, so then we know that it converges. So we know that the sum is equal to a over 1 minus r. So let's just plug in some values. We got a equals 1/2 right here. We got r equals 1/2, so 1/2 over 1 minus r, which is also 1/2, equals 1/2 over negative 1/2. Oh, JK, equals 1/2 over 1/2 equals 1. Does anyone have questions on this problem right here? So this converges, and its partial sum, or its the answer, I guess, so to speak, is 1. Okay, does anyone have any, like, I'll just keep reviewing. This is going well, and I'm sure you guys could probably use this review time. If you do have a specific question on anything, Like, I do mean anything. Feel free to type it into the chat. I'll look at it. But until I get a specific question, I'm just going to keep reviewing what we've been doing. I'm going to make sure everyone is comfortable with infinite series, and then we'll call it a day. So let's go on to, here we go. All right, let's work with the direct comparison test for divergence and convergence, and then we'll also look at the limit comparison test. So this right here, I briefly touched in on last time. So what I'll end up doing is work a couple more problems and maybe make life a little easier for some of you guys. I say maybe because I only have so much control, you know? Like, I can tutor and teach and SI all day, but at the end of the day, I am not the one that has to take the test. But this right here will make said hypothetical test a lot easier to do. All right, I think I defined these two last time, so I said, oh, you know what? I have a perfect example for this, actually. Let me grab my phone so I can pull it up real quick. But this is, if any of you are like, I made a math TikTok just because I got bored and Haley always likes to send me those things through text. So I figured I'd cut out the texting and just download the app. But if any of you follow my math TikTok, I worked this problem on it. And it's, let's see, we got here, n cubed, n plus squared, n plus 1. So this is a great example for both the limit comparison test and the direct comparison test. We got n equals 1 as it approaches infinity for the function of n times the square root of n plus 1 over n cubed. So we can simplify that by canceling this and turning this into a 2. So then we get series n equals 1 as it approaches infinity for the square root of n plus 1 over n squared. Okay, so now you're probably like, wow, that looks pretty rough. Don't know how I'm feeling about that one. But it's not as bad as it would seem. So let's do, so you guys remember, right? Convergence, direct comparison test for convergence is if we have a function b sub k that converges is greater than or equal to a sub k, which is greater than 0, then a sub k converges if b sub k converges as well. So let's try and think of a function here. And by the way, when you see a problem like this, you don't even really have to care about the constants because things at infinity, what's a plus 1 going to do is not going to do a whole lot. So what I like to do for writing my comparison test is I just look at the values of n. So I can change this right here, right? Because I'm not limited on what I can choose for b of k. As long as it's greater than or equal to a sub k, it is fair game. So let's try this. So we got, what would be a fun one? Let's just write this as root n over n squared. So that's equal to 1 over n to the 1.5, because I know all of you hate fractions. But let's think, does anyone, so I'm sure a lot of you guys are actually really confused on how you choose stuff to test for it. And honestly, it's like U substitution or integration by parts. The more you do it, the easier it'll be to understand. Like that tip I just gave you about looking at the variables instead of the constants. That's something a lot of people have trouble with because they just see a bunch of numbers and letters and it's like, oh man, infinity's a real large thing. So let's think about this logically then. So 1 over n to the 1.5. So let's just test a few values of n. Make sure this all works out. So we'll do n equals 1, and we'll call this right here equals b sub k. We'll use that. If it doesn't work out, then it doesn't, and we can change it to a different value, right? So we'll call this a sub k right here. So for n equals 1, a sub k equals the square root of 2 over 1. So that's equal to the square root of 2. And then for n equals 1, for b sub k, we get, let's see, 1 to the third, so we get 1. So the square root of 2, would you guys say that is less than, equal to? What are your thoughts? So obviously, square root of 2 is not less than 1, right? So Hmm. 1 over n. Let me think about this one. So root n plus 1 over n squared. Oh, wait a minute. I'm being really stupid. No, I'm not, because this is not one. N plus 1. So this is tricky, guys. Like, if sometimes it takes a minute to kind of figure out a value of b of k. If you have one and you're just watching me struggle, feel free to shout it out. But give me a second, because this is actually, it might be beneficial for you guys to kind of watch my process for this. So let's think. So 1 over n to the 1.5, that b of k does not work. So then there's a couple things we could do. God, I really wanted to do the direct comparison test, and now I want to do the root test, but let's try and just untask here. Okay, so root n over n squared, duh, that's going to be less than that. Okay, so what if we did root n plus 2? That's greater than that. Yeah, that'll work. Now I guess we could do limit comparison test. Or what we really need to figure out is, does this one converge? So let's prove that this one either converges or diverges. So limit as n approaches infinity, we'll just do the test for theorem divergence test, which is just limit as n approaches infinity, the square root of n plus 2 over n squared. So that's obviously going to be equal to 0 right there, right? So that doesn't tell us if it diverges or converges, which is kind of a useless test right there, but it does have its purposes, because when it does diverge, it saves you a lot of steps. So now we need to do more tests. So I'm going to give you guys a second to work on this real quick and see if anyone can come up with the answer, or maybe not. I don't know. How are you guys feeling? Like what do you guys exactly want to work on? Would you guys, you know what, hold on, I'm gonna finish this up. Okay, you know what? I just figured it out. I remembered why I'm being an idiot right now. Where's my eraser? Oh, I'm changing to a white towel now instead of a green one. I don't know why I just erased everything, but screw it. The bridge is already burned. I'm gonna finish. Okay, so n cubed, so then this is equal to n equals 1 as it approaches infinity, or square root of n plus 1 over n squared is equal to a sub n. So we'll define b sub n as, let's think, root 2n over n squared. Yeah, this right here is why it's kind of tricky to figure out the b of n values, because you really got to think about it. Like, you got to plug in some numbers. It's not always going to work. The more you do it, the quicker you'll be at it. Like this right here, I mean, I wouldn't have thought of that off the top of my head. I'm sure some of you might have, because some of you have been doing this a lot, I bet. But this stuff is actually kind of tricky. Like, it's a lot like everything else we've done this entire semester, where you just have to do it 1,000 times to get any good at it. But there are some tricks and tips. Like if you think about it logically, we could think about it as a fraction, right? So we know that root n plus 1 over n squared. So we know to make a function that's bigger than that, we either have to decrease the denominator or increase the numerator. And in this situation, I increase the numerator, because 2n is always going to be greater than or equal to n plus 1. If you don't believe me, you can test a few values here. So let's do this. So n equals 1, then a sub n equals root 2, and b sub n also equals root 2. So a sub n and b sub n are equal. So now we can do n equals 2. So then we know that a sub n equals root 3 over 4, and then b sub n equals 2 over 4. Wait a minute. Yeah, because the square root of 4 is 2, which is equal to 1/2. So b sub n is greater than a sub n. So now what we're going to do is we're going to see if b sub n converges or diverges. So the first thing we could do is test for divergence, but that's going to give us 0, because limit as n approaches infinity. The denominator is greater than the numerator by degree. So we already know that this would give us 0, and that test for divergence wouldn't work in that situation. So we could change this into a p-series, right? I mean, we could just write this as root 2 times limit as n approaches infinity. Or actually, no, we don't even need to do that. We can write it as a series. So root 2, the infinite series, n equals 1 as it approaches infinity, times root n over n squared, which equals n to the 1.1 over n to the 1.5. I know I'm kind of getting clustered down there. But p-series, p is greater than 1, so it converges for b sub n, or b of n. So now we've proved that a sub n is less than or equal to b of n, and we know that b of n does indeed converge. Thus, a sub n converges. Does anyone have any questions on this? We'll leave it up for another couple, like 20 seconds or so, and then we'll jump into alternating series, do a limit comparison test somewhere in there. Oh, you know what? I was about to explain the limit comparison test. That'll work perfectly. Okay, so limit comparison test for this, which I guess you technically do kind of have to do, is if you can show that the limit, that they both meet at the limit, at the same limit, and then here, I'll draw it out. So let's say red is a sub n, right? So we'll say it's going down there, approaching, we'll say it's approaching 0, something like that, right? This is just a made up example here, just to kind of prove a point. And then we'll say green is b of n. So we know that b of n in this situation is obviously greater than a sub n. So if we can prove that they both converge to the same point, and we know that one of them is, if we know that the limits both meet at the same point, and we know one of them converges or diverges, then we can use the limit comparison test to prove that the other one converges. I personally prefer the direct comparison test, just because I think it's a lot easier. But if you really, really want to show your work, what you could do is you could do the direct comparison test and then verify that they are equal to each other by doing the limit comparison test. But if you plug in values for A sub n and B sub n and just kind of show that, that should be more than enough. Like I would recommend using the limit comparison method for at least 10 to 20 problems, just so you have a feel for it. I mean, there definitely will be a couple questions on the test, but most of them I'm assuming are going to be like, does this series converge? Where does it converge to? She might even ask you to find the sequence of partial sums. And of course, there will always be integration on our tests. And then this one, I'm guessing it'll take the form of the integral test, which, by the way, you guys use way too much because that was my least favorite series test. And if you know how to use the direct comparison, you really don't need to know how to use, or how to, no, that's not true. Both have their time and place, but I have a feeling a lot of you are using the integral test for pretty much anything that you get. Tell me if I'm wrong, but I know a lot of people in my Calc 2 class did that. Okay, and it's not efficient. I mean, if you can do the direct comparison test, or like you're going to be a whole lot faster than everyone else. Like I've been doing these problems maybe, I don't know, 5 steps of work, and that's more than enough work that I'm showing. Like you have to prove that it works, but you don't have to overprove it. Like don't think you have to use every theorem for every problem. You literally, as long as if it's proved, it's proved. You just have to know the theorems. The biggest thing for this class, or for this portion of the class, so to speak, is definitely knowing the theorems, because they will save you a lot of trouble. But now, to just finish up kind of today, I'll introduce our alternating series, and then we'll pick up tomorrow with all the new stuff, and tomorrow we can introduce stuff like power series, probably not quite power series, but no, not quite power series yet. We'll stick with the basics this week. So tomorrow we'll do the root and ratio test. We'll do a bunch of different types of problems. And then if I hold a session on Sunday, we can definitely start working on power series and maybe even introduce Maclaurin series, which really a Maclaurin series, I'll save that for the next time. I'm trying to not get too distracted here. But yeah, so right now we're just going to introduce alternating series. You've definitely already seen one, because I think one of the quizzes we did had one. Is she asking you guys to find the error for convergent alternating series? Sheesh. Okay, well, I'll just kind of wrap it up here, and I'll give you guys the definition of the alternating series test and how you can figure out if it's convergent or divergent. So let's see what we got here. We got the series k equals 1 to infinity for the function -1 to the k plus 1 times a sub k. It's going to equal, let's see, a1 minus a2 plus a3 ... minus plus. That's why it's called an alternating series. So there's 2 things you need to make sure for this one, and one of them will seem familiar, one of them may seem familiar. Let's find out. So limit as a sub n approaches infinity for a sub n. So limit as n approaches infinity for the function a sub n has to equal 0. Or wait, yeah, has to equal 0. So that's one of the conditions for this theorem. And then the other condition, and this is to see if it converges or not. And this is absolutely convergent if it passes this test. And then you also have to prove that a sub n is non-increasing. And if you guys remember our monotonic sequence test, then you'll remember this. It looks something like this. A sub n plus 1 non-increasing. So I guess we'd have to say is less than or equal to a sub n. Yeah. So if all of those are met, if both conditions are met, then this is absolutely convergent. So there's a proof for it. I don't think you guys are really at a point where you need to be working with proofs, especially considering we haven't done one this entire semester. But yeah, there's a couple things. I mean, one thing I'll do, just really, this is the last thing for real this time, is let's see what we got here. Oh yeah, this is gonna mess a lot of y'all up. So we got -1 to the k plus 1 over k. And this is called an alternating harmonic series. So this right here, the biggest thing about alternating series that you need to remember is that there's a proof for this too. I don't know if you guys want to work it out or not, but alternating harmonic series converge, which is very different from a regular harmonic series because, as we all know, a harmonic series diverges, but an alternating harmonic series converges. So I think that'll be it for today. I'm going to stay on live for a couple more minutes in case anyone has a question they want me to work on the board, anything like that. If you guys have any last minute questions, now's the time because I'm about to wrap this session up and call it a day. So I'll leave it open for, I don't know, like 5 more minutes, 3 more minutes, 3 to 5 more minutes. And just ask any questions you'd like me to work, or if you don't want me to use this green marker, I understand that it could be kind of hard to see. Just any questions, comments, concerns, I'll stay on for 5 minutes and let you guys type. Or if you don't like typing on YouTube's format, then you can do it in the group chat as well. I have very little preference on this matter. All right, well, I'm just gonna write out what we're doing next time. And then I guess we'll call it a day. I'm not using this green one. I'm gonna use red because that's probably the easiest for y'all to see. So next time we're going to be finishing alternating series. Let's see, then we'll do root and ratio test and intro power series, if we have time. I will see y'all tomorrow. Thank you for coming to the session, and I hope you all are staying safe and washing your hands. Till next time, this is Nate.